This video will cover section 6.3, vectors in the plane. The objectives for this section will be to represent vectors as directed line segments. Also to write the component forms of vectors and to perform basic vector operations such as addition, subtraction, and others, and represent them graphically. Also scalar multiplications, which is like multiplying a vector by a number, by a constant, and this could be positive or negative, just so you know. Also to write the vectors, write vectors as linear combinations of unit vectors. For that we will use the unit vector I and the unit vector j. Also to find the direction angles of vectors. And finally, to use vectors to model and solve real-life problems. So, quantities such as force and velocity, involve both magnitude and direction. Magnitude and direction. Well, one is the magnitude and one is the direction, and cannot be completely characterized by a single real number. So to represent such quantity, we can use a directed line. So if your line has magnitude, which will be the length of it, and the direction with respect to, I don't know, a horizontal line or the origin, then if it has those two things, it will be the directed line, and it will have an initial point, and then it will have a terminal point. So we use vectors to represent things like force and velocity. Those are two, but also in the next section we will cover the vector of work, which is a force vector. The directed line segment PQ has initial point. It will be the first letter that you see here, and then the second letter will represent the terminal point. And the little line on top with one arrow, we could call it a ray, but we're gonna refer to it as a line segment or a vector. Now, like I told you on the previous slide, the magnitude will be the length, and it is denoted by the same as the PQ with the arrow on top, but we're gonna use a double vertical line on each side, and that's what we're going to use to denote magnitude. And what we're going to use to find the distance between 2 points will be the distance formula. To refresh your mind, distance is a square root of just like Pythagorean theorem, but instead of having A and B and looking for C, you're looking for D. You can call distance anything you want. In this case, we're going to use the name of the vector and, of course, those two vertical lines on each side. And we're going to be finding the difference between the x coordinates and squaring that, and then adding that to the square of the difference of the y coordinates, like so. Okay, so two directed line segments that have the same magnitude and direction are equivalent. So in some questions we will be given two vectors, and perhaps they might not have the exact same location with respect to their initial and terminal points. But if we calculate the magnitude, which is the length, by using the distance formula, And if they have the same magnitude and the same direction, which will be the angle, we will consider those two vectors equivalent. And we will do an example in a minute. So you could see all the vectors here. Each line represents one vector, or in this case, the PowerPoint is referring to that as a line segment. And you could see that they all have the same length, and they are all pointing to the same direction. For example, if I was to draw a horizontal line here, and we were to calculate the angles that each vector makes with that horizontal line, it will be the exact same angle. If I draw a parallel horizontal line to it, like that, we could see all the angles that you see here will be the same. But we will get to direction angle in a minute. Okay, so next slide. The set of all directed line segments that are equivalent to the directed line segment PQ is a vector B in the plane written. For this class, we will stick to the XY plane that you're all familiar with. And we call that R2 because it's a two-dimensional plane. But if you do take Calc 3, you will study vectors in R3. And so those are the three-dimensional vectors, and we include an extra axis. Of course, if we were able to rotate it, which you could do that with some apps, all three of them axes are perpendicular to each other. So that is the difference, and that is what it will look like in a three-dimensional place. So that will be something that you will do in Calc 3, and if you take linear algebra, you'll use those there as well. So going back to this course, we will use lowercase bold-faced letters. So that's what you could see on WebAssign and your textbook. So bold letters and lowercase to denote vectors. So remember from the previous two sections, we used to use uppercase letters to denote angles and lowercase to denote the sides of triangles. So in this case, we will use lowercase, but also bold letters, or bolded, so that you know that we're talking about vectors. Okay, so we have our first example here, and we have two vectors. Each line segment represents a vector. You can see their initial points will be here and here, and then their terminal points will be here and here. And so the coordinates are also visible there. So we're actually going to be using those to check if they are in fact equivalent. That is the question. So we need to find two things. One of those is magnitude. And so for that, we will be using the distance formula. So remember the symbol for magnitude. Let's work with vector u first. And we will have those double vertical lines on each side. And so it will be the square root of the difference, the square of the difference of the x coordinates. So in this case, for vector u, the x coordinates, it doesn't really matter which way you choose to enter them, but I'm gonna choose to enter 3 first and then -0. Because if I have and actually it does well, since this is the initial point, not that it matters that much, but as long as you don't switch your coordinates, it's okay. not switch, but mix and match. So if this is x1, y1, then the other one should be x2, y2. So we have 3 minus 0, and then we're going to have 2 minus 0. Remember the distance formula. That is what we're using. And from here, first we subtract, we do what's inside the parentheses. So 3 minus 0 is 3. Then we will have 3 squared plus 2 minus 0 is 2, so 2 squared. From here, we will get the square root of 9 plus 4, which is the square root of 13. So now let's go ahead and do the same thing, but for the other vector. So that would be vector v. So we're going to need the square root of the difference of the squares. Actually, I said that wrong. But okay, we're going to substitute. I'm going to write the distance formula here. So if we're looking for, let's say, the magnitude of a vector, it will be x sub 2 minus x sub 1. That's the difference of the x values. We square that, and then we add the square of the difference of the y values. There we go. That sounds better. So let's go ahead and substitute. Now we're working here with the other vector, and we will take the, let's consider the terminal point. That will be our x2 and y2. And here this will be our x1 and y1. So we're going to have 4 minus 1, and then we will have 4 minus 2. Okay, and we need to do what's inside the parentheses first. So this will be 3 squared, because 3 minus 4 is 3. Then 4 minus 2, that is 2, and we need to square it as well. So we'll have the square root of 9 plus 4, and that will give us the square root of 13. So we have checked that, yes, they do have the same magnitude, but now we have to check for direction. And so to check for direction, we're actually going to use the slope formula. So for, let's see, the vector, I'm going to call it m sub u. So we know that's the slope of vector u. So it will be 3 minus 0. Oh, sorry, that is completely wrong. Actually, I'm going to write the formula here. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So remember, y values need to be on top. So it will be 2 minus 0 over 3 minus 0. So that will be 2/3. Now we're going to do the same for the other vector, and this is positive, which is very important. And you can tell that because the line, or the line segment, is leaning to the right. So it makes sense that it does have a positive slope. So now let's calculate the slope of the other one. So it will be m sub v for the slope of vector v. So that will be 4 minus 2, the y values on top, subtracting, and then the x values on the bottom, 4 minus 1. And so that would be 2/3, also positive. So now that we have checked that they do have the same direction and the same magnitude, then we could say that they are equivalent. So this is true. The directed line segment whose initial point is the origin. Remember, we had an initial and a terminal point. So if it is if the initial is located right at the origin, which is at 0, 0, the intersection of the x and y axis, is often the most convenient representative of a set of equivalent directed line segments. This representative of the vector v is in standard position. So if your initial point is the origin, we refer to that vector as in standard position. A vector whose initial point is the origin, 0, 0, can be uniquely represented by the coordinates of the terminal point. So if we say the vector is in standard position, we already assume right away the initial is 0, 0 at 0, 0, and so we just need to know the terminal point so that we could represent the vector and know exactly where it is located with respect to the origin. This is the component form of a vector v, written as v equals, remember here with the lowercase bolded letter, and then we have here the horizontal component, which is v sub 1, and then the vertical component, which is v sub 2. Just think of it as your x and y value for now. And different notation or new notation, you might have seen it before. We have this little, I don't know what to call them, brackets, vector notation. That's what we're going to be using for this class. So remember, we refer to this as the component form, and we only need the terminal point. So the coordinates v sub 1 and v sub 2 are the components of v, the horizontal and the vertical, in that order. If both the initial point and the terminal point lie at the origin, then v is the 0 vector. So it will be something with just a dot, because if it's in standard position, we know the initial point is there, and then it just happens that the terminal point is also there, so we call that the 0 vector, and that's how we will refer to it. So the component form of a vector, if a vector is not in component form already, what we're going to do is subtract some of the values that we have here. So here, instead of using x sub 1, y sub 1, we are using p and q. So let's go over that. So if we have a vector of this form, remember we started using this type of notation. So the initial point here is the letter P, capital, and so we're using for the components the lowercase p sub 1, p sub 2. But I want you to think of it in terms of x and y. That's what we're talking about. We're talking about horizontal and vertical components of the vector. So now for the terminal point, we have the point Q, and so the horizontal component is Q sub 1 and the vertical component is Q sub 2. So this is similar to saying x sub 2, y sub 2, but in this notation for this book, we use the letters P and Q, and if you notice, both the horizontal and the vertical component have the same lowercase letter as the uppercase letter that is representing the point. So that's why it looks like that. But if you don't want to think in terms of x and y, just think in terms of horizontal and vertical components. So here we get the difference of the horizontal component, and here we get the difference of the vertical components. And that's how we turn a vector into component form, which will be here. Remember, that will be with this will represent the terminal point. If we were to just shift the initial point of the vector to the origin at 0, 0. Now, again, to get the magnitude of a vector, we use the distance formula. We use the double vertical line to indicate that's the magnitude, and that will be the square root of the difference of the horizontal components square plus the difference of the vertical components square. And if we already have our vector in component form, then it's just enough to square just with the, remember, this will be the terminal point. If it's in component form, the terminal point is represented by v sub 1 and v sub 2. And that is because we know the initial point is at 0, 0. So then it is enough to square the horizontal component like we see here, v sub 1 square, and then plus the square of the vertical component, which is v sub 2, and then we take the square root. And so that is exactly the same thing. So that's why it's more convenient to have a vector in component form, because it's just like a lot easier to manipulate. So we're going to go over some special vectors, such as the unit vector. And unit, for one, is a vector with a magnitude equal to 1. So that we call the unit vector. And then we have the zero vector, which is the one with a magnitude of 0. And we call that the zero vectors, like the one that we have here. So if we have two vectors, and if we are saying that those two vectors are equal to each other, if we say if vector u is equal to vector v, that will happen if and only if the horizontal components are equal, and also the vertical components are equal. So for that, we could say that the two vectors are equal. And the if and only if, it works as a double conditional statement. So it means that from left to right it's true, and also from right to left. So if we were to start by saying the vertical components are equal and so are the horizontal components, then we can say for sure that the two vectors are equal. So here we have an example for this vector at vector u, that it's at 0, 0 initial point, and terminal point is at 3, 2. So we calculate the difference of the horizontal components to have it written in component form. This will be the component form, and you can already see the answer for the other one. It's going to be the exact same thing, even though we do not have the same initial points or the same terminal points. You could see that clearly. However, when we apply the process to turn them into that component form, then you could see how if we subtract 3 minus 0, that's what we have here, we get a 3. And if we subtract 2 minus 0, what we have here, we get a 2. If we do the same with the other vector, we have two vectors here. One is u, one is v. And if we do the same thing, we subtract 4 minus 1, which we have here, and then 4 minus 2, which we have here. So then we could get also the same component form as the other vector, as vector u, which is 3 and 2, 3, 2. Remember that represents the terminal point if the vector was to be placed at the origin. So it will have initial point there, and then terminal point will be here. So it will be graphed that way. So now we're going to find, for example 2, we're going to find the component form and magnitude of the vector of vector v that has initial point 4, comma, -7 and terminal point at -1, comma, 5. So from here, we could say that this will represent P1 and P2. And then here, this will be representing Q1 and Q2. And I'm saying that because I'm going to call this point, this is going to be point Q. So that's why I'm using the lowercase letters here. And then here, I'm going to refer as my initial point as point capital P. So that's why we have that lowercase here. So I'm showing you that because those are the same letters that they're using here. So now if we want to find the first one is, the first operation will be to find the horizontal component. So that will be Q sub 1, which is -1, minus P sub 1, which is +4, and that will equal to -5. And now we do the same for the vertical components of the vector. And we will have Q sub 2, which is +5, minus P sub 1, which is -7. So notice how I'm going to use parentheses here because the formula already includes a negative. And so I don't want to oversee that I have a double negative here because this will be 5 plus 7, which is equal to 12. So now for the component form of this vector that had initial points here, terminal point here, is going to be, the notation will be -5, comma 12. And this means, remember, in component form, it means that the initial point is now the origin at 0, 0, and the terminal point has been shifted to the point -5, comma 12. And that is the component form of the vector.